I love when the universe, just throws us a complete curveball. It forces us to admit we really don't know everything. It kind of reminds me of the biological platypus.
Oh, the platypus.
Yeah, that mix of duck, reptile, and mammal traits that just shouldn't belong in one creature.
It's the perfect analogy, actually.
Well, it seems astronomers just found the cosmic equivalent.
They really did.
Mm-hmm.
This is a discovery by Hao Jin Yang and his collaborators. They're calling it astronomy's platypus.
Okay, I'm hooked.
So we're talking about 9 objects. They're called ultra-compact high-redshift galaxies, or UCHRGs for short.
A mouthful.
It is. They found them in archival JWST data, and these things are at redshifts that place them about 12 to 12.6 billion years in the past.
So we're seeing them when the universe was only, 1 or 2 billion years old?
Barely. It's ancient history.
And here's the core paradox, right? If you find something that's extremely point-like, that far back,
You think quasar.
you think quasar, a huge active black hole. But what are these things doing to break that mold?
They break it in 2 pretty major ways. First, they look like stars, sure, but their energy output is, well, it's modest.
But how?
Kind of comparable to our Milky Way today, not the brilliant blaze of a quasar.
Mm-hmm.
And second, the light they emit tells a completely different story.
Okay, let's unpack that. The point-like part.
Yeah.
In the raw JWST images, how tiny are we actually talking about?
Oh, they're staggeringly small.
Really?
I mean, when we measure an object's size, we use something called the point spread function, the PSF. It's basically how sharp a single point of light looks.
The telescope's resolution limit.
Exactly. And these galaxies are barely larger than that. So concentrated that most of their light comes from a region less than 1,000 parsecs wide.
For perspective, our Milky Way's visible disk is tens of thousands of parsecs wide.
Precisely. These are like tiny cosmic knots of matter.
That compactness just screams, black hole! But you said their light, their spectrum, says something else. Why does it rule out a typical quasar?
It's all about the width of the emission lines. When a black hole is feeding, the gas swirling around it is moving chaotically at thousands of kilometers per second. That motion smears the light out, creating really broad spectral lines.
And these don't have that.
Not at all. These platypus objects have very narrow emission lines. It suggests much calmer, more organized motions, only a few hundred kilometers per second.
So that just immediately rules out the typical broadline quasar idea.
Right. And yet they are screaming with intensity, aren't they?
The star formation must be explosive.
It is. They have extremely high equivalent widths for markers like oxygen-3 and H-alpha.
Which are signs of violently energetic star-forming regions.
That's right. They're like local green key galaxies in terms of energy. But they've crammed all that activity into this super compact ancient package. It's that clash, between the shape and the spectrum that makes them so hard to classify.
It's just incredible how much data JWST is producing. You're trying to classify objects based on 2 totally conflicting data sets?
And you have to synthesize it all so quickly to keep up.
Yeah. It really speaks to the need for advanced systems to manage it all.
Mm.
And speaking of critical data, this deep dive is sponsored by Embersilk. If you or your organization needs help with those kinds of advanced systems, we're talking AI training, automation, integration, or software development, Embersilk has the expertise. They can help you uncover where AI agents could make the most impact for your business. Don't drown in data, automate your ascent. Just check out embersilk.com for your AI needs.
A very fitting sponsor.
So diving back into our compact galaxies, the leading idea is that they are these extremely young, hyper-efficient, star-forming cores. What does that mean for, the big picture of cosmic evolution?
I think this is the most exciting part. It suggests a previously unrecognized phase in how galaxies form.
Whole new phase.
Yes. For a long time, we focused on the chaotic merger model, where early galaxies were built by these aggressive, violent collisions.
Right, smashing together.
Yeah. But if these are purely star-forming cores, they must have formed in a quiet way, perhaps through a monolithic collapse. It would mean the blueprints for the earliest cosmic structures were fundamentally different than we thought.
So a significant chunk of early galaxy building might have been quick, internal, and quiet.
And we've just been missing that entire part of the story.
Wow. So JWST isn't just showing us known things better, it's finding entire populations we never even knew existed. It's filling in huge gaps in the cosmic timeline.
Precisely. This discovery just opens up such a hopeful new avenue for research. And it really raises an important question for you, the listener.
Okay.
Now that we know this compact population is out there, the next step has to be higher resolution spectroscopy. That will help us confirm if they are truly these quiet starbursts,
Or, what's the alternative?
or if they might be hiding a totally new population of very weak early black holes. And either way, finding out will totally change our understanding of how the very first building blocks of our universe came to be.
What a fantastic place to leave it. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.